Hey guys, this is section 10.3, experimental and theoretical probability. So two different types of probability that we're going to talk about today, but we're still going to use our the same probability rules that we used last section. So experimental probability is based on repeated trials of an experiment. So just like last time, we can write probability as a fraction. So you write the number of times the event occurs over the number of times of trials. We use experimental probability when we can't always predict or we don't always know what's going to happen. So experimental probability is actually commonly used in sports. So anytime you're looking at some sort of statistic, let's say you have a free throw percentage of 72%. Well, that means you make 72 out of 100 free throws. That percentage changes every time you make or miss a free throw. It's going to go up or down. So experimental probability is always changing because the number of times the event occurs and the number of trials is always changing as well. So let's look at this first example. It says, find the experimental probability. Write your answer as a fraction and as a percent. Anthony has 14 hits in 30 at-bats. What is the experimental probability he gets a hit in his next at-bat? So we're calculating the number of hits that he gets, right? So we're going to say the probability of him getting a hit. And so far, his stats say that he's gotten 14 out of 30 hits. So we just write that fraction down, 14 over 30. That fraction, of course, reduces. You can divide by 2 to get 7 over 15. So he gets a hit 7 out of every 15 at-bats. Now we can turn 7/15 into a percentage by doing 7 divided by 15, top divided by bottom, and getting a decimal, and then sliding that decimal point over twice. So we get 0.46 repeating, which is going to be 46.6 repeating. I'll just say 46.7 is what it would round to if I go to the nearest tenth. 46.7% of the time, which is actually really good. That'd be a really good batting average for baseball. Example B says that Melissa has made 18 out of her last 21 free throws. What is the experimental probability that she makes the next free throw? So we're calculating the number of free throws here. I'll just use FT, the probability of getting a free throw. And she's hit 18 out of 21. So we're literally just taking the information they give us and turning it into a fraction. Now I'm going to reduce this fraction by dividing by 3, and that's going to give us 6 over 7. And then we can turn that into a percent by doing 6 divided by 7, which is 0.857, and quite a few other decimal places. But we'll say it rounds to 85.7%. That's a pretty good free throw average. So again, we're just using the information they give us. 18 out of 21 is our probability for Melissa, and 14 out of 30 was our probability for Anthony. We're just reducing that fraction and turning it into a percent here. So since experimental probability is based on observations, the probability changes after each trial, just like I mentioned. So it says Melissa missed her free throw. What is the experimental probability that she makes the next one? Well, she'd hit 18 out of her last 21 free throws. So if she missed this next free throw, it's going to drop her, so probability of the free throw, it's going to drop her probability to 18 out of 22. She's taken one more shot, but she missed it. So she still only made 18 out of 22. And then that reduces by 2 to 9 out of 11. And that's going to lower her percentage. Obviously, if she missed it, it's going to lower it. And that's going to lower it to 81.8%. That's what 9 divided by 11 is. It's 81.8% or 0.818. So it's going to drop her free throw percentage down. Now, if she makes the next one, it's going to then raise it. If she makes the next one, now she'd have 19 out of 23 free throws. And so this just continues to go on and on and on. And that's why experimental probability is always changing, because the more observations we get, the better the understanding we have. That's why if you, which we're not watching baseball right now, unfortunately, because it's been postponed, but I like watching baseball, especially at the beginning of the season. Everybody's stats are so overinflated. You know, you have 2 games and Anthony Rizzo goes 2 for 3, and then the second game he goes 3 for 4, and he's got this really, really high batting average. And then as the course of the season goes on, that batting average is going to drop back down to what's typically pretty average, right? Because the more trials we have, the more observations, the better the stat, or the more understanding we have of the stats. Now, experimental probability is also called relative frequency. It's also referred to as relative frequency. The relative frequency is the fraction or percent of the time the event occurs. So it's exactly what we've been doing. You're going to have some homework problems that ask you to find the relative frequency, and just remember that's the same as the experimental probability. Take the number of times the event occurred over the total number of times that the experiment was conducted. So this question is straight out of the homework. We're spinning a spinner. I'm asking you some different questions that aren't in the homework, but you may want to refer back to this example as you're working through the homework. It says a bar graph shows the results of spinning a spinner. What is the relative frequency? The first thing we want to do is figure out how many times the spinner was spun, and we're not given that information. So a 1 was spun 8 times, a 2 was spun 6 times, 9 times was for 3, 11 for 4, a 5 was spun 9 times as well, and then a 6 was spun 7 times. So I'm just going to add these up. I know that 11 and 9 make 20. There's 14, so 34, and then I know 9 and 7 make 16. So 34 and 16 makes 50. So we have 50 total spins. I'm going to write that down so we have that. Now it says spinning an odd number. So I'm going to erase this so we can still work with this. Spinning an odd number. Our odd numbers are 1, 3, and 5. And so we had 8 ones that were spun, 9 3s, and 9 5s. And so if you add that up, 9 and 9 makes 18, and 18 and 8 makes 26. 26 out of 50 spins were odd numbers. And then we can divide by 2 to reduce this to get 13 out of 25. And that would be our reduced answer. And then it says spinning a prime number. Well, our prime numbers, remember the word prime means any number that only has only has 2 factors. So numbers that have 2 factors on this list, 1 only has 1 factor, and that's not prime. 2 times 1, 3 times 1, and 5 times 1. Those are 5 prime numbers. We can't use 4 because you can also do 4 times 1 and then 2 times 2. And we can't use 6 because we can do 6 times 1 and 2 times 3. So 4 and 6 aren't prime. And so 2 was spun 6 times, 3 was spun 9 times, and 5 was also spun 9 times. And so 9 plus 9 is 18, plus 6 is 24 out of 50. And we can reduce that by 2 to 12 over 25. It's a little bit less likely that we get a prime number. And then this last one here says not spinning a 2. Now, I'm going to save you some time here. If you get a problem like this and it says not spinning a 2, your instinct is going to want to be to add up how many 1s, 3s, 4s, 5s, and 6s there were. There's an easier way to do it. If a 2 was spun 6 times, and there was 50 spins in all, 50 minus 6 means that not 2, or any other number but 2, was spun 44 out of the 50 times. We don't have to add up all the other ones. We can just subtract how many times a 2 was spun. And then if we divide by 2, we get 22 over 25, so a good chance that we get a number that's not a 2. Now you're going to have some homework problems, some more homework problems that deal with this same exact graph, this same chart. So just remember that this might save you some time, there was 50 total spins, and then we're just going to keep using that number in our denominator, and then if it reduces, then go ahead and do that. So one thing that we'll do, and we've already been doing this, but we can use experimental probability to make predictions. You've already been doing some of that in your other homework where you've been setting up a proportion to make a prediction. This question says, at a clothing company, an inspector finds 5 defective pairs of jeans out of a shipment of 200. If this trend continues, how many pairs of jeans would you expect to be defective if a shipment had 5,000? So if there's 5 out of 200 genes that are defective, then if that continues, how many out of 5,000 would be defective? And again, we're just going to set up a proportion and cross multiply. 200 times x, 5 times 5,000. Now 5 times 5 is 25, and then add 3 zeros there. And then we're going to divide by 200. And if we divide by 200, go ahead and jot that down here. We're going to get x equals 125 defective genes. Okay, so quite a bit, but again, it's out of a shipment of 5,000. That's still the store would probably want to do something about that. They don't want to ship that many bad genes off. Okay, here's another sports question. It says, quarterback Dak Prescott completes 68% of his passes. How many passes would you expect him to complete out of 350? There's really two different ways we could do this problem. We could continue using a proportion, and we could just say 68% is 68 out of 100. So if he completes 68 out of every 100, how many is he going to complete out of 350? And we could cross multiply that. Or we could say if he completes 68%, you can see that word of right there, of his passes, and he's going to pass 350 times, then I could just do 0.68 times 350. And if you type that into your calculator, you'll get 238, and we'll call them completions. So again, we're just using experimental probability or statistics, right? When we're talking about sports, it's just really the statistics to make predictions. And people do this all the time in sports. You play the first 4 games of the football season and they say, oh, he's on pace to throw 55 touchdown passes. And they use this all the time. So if you like stats and you like sports statistics in particular, then you use proportions all the time and use probability all the time when you do that. And so if you're thinking about getting a career in sports science or something like that, then mathematics is going to be super helpful for you. All right, so that was experimental probability. Let's talk about theoretical probability now. Theoretical probability is what you know should happen. It's based on theory, not on observation. So the probability problems that we did in our 10.2 section when we rolled the number cube, that's all theoretical. We know what should happen. And so this little thing right here that I wrote down, that's exactly what I put in your notes from last time. So let's look at this example here. You spin the spinner. What is the theoretical probability of spinning a 4? So the probability of spinning a 4, we write it like that, P parentheses 4. There's only one 4 out of 6 spaces, and that doesn't reduce. That's it. That's all I have to do. It's just normal probability. The next one says spinning red. Well, there's 2 red spaces. Put that in here, red. There's 2 red spaces out of 6, which is going to reduce to 1/3 as our final answer. So that's really easy. Theoretical probability is what we've been doing for a couple sections now. So we can also use theoretical probability to make predictions. We're just going to use it to set up a proportion, just like we did in our last problem. So the theoretical probability of spinning a prize wheel and winning a bobblehead is 1/6. 1 out of 6 people will win, theoretically. If the wheel is spun 540 times, how many bobbleheads do you predict will be won? Well, if 1 out of 6 people will be winners, then how many out of 540 people will be winners? That's it. That's all I have to do. And then I cross multiply. 6x equals 540. And then divide by 6. 6 goes into 54 9 times, goes into 0 times. So we would expect to have 90 winners. Now this next example is from the homework number 13. It says there are 105 lettered tiles in a board game. You choose the tiles shown. How many of the 105 tiles would you expect to be vowels? Well, if I randomly select this grouping, I picked, let's see, there's 7 tiles here. All right, 4 and 3 make 7. And 1, 2, 3 of them are vowels. So if 3 out of 7 tiles that I randomly picked are vowels, then how many out of 105 tiles would I expect to be vowels? And so again, we're just making a prediction. We're going to cross multiply 7x. 3 times 105 is 315. And 315 divided by 7 is 45. So I would expect there to be 45, vowels in the game. And if I draw out a different grouping of tiles next time, this could change, but that's my prediction right now based on the theoretical probability. Number 23 from the homework is also going to have us make a prediction. The theoretical probability that a pop song plays on your MP3 player, well, that's kind of dated. Everyone's got an iPhone now, is 0.45. There are 80 songs on your MP3 player. How many of the songs are pop songs? Again, I could turn this into a fraction and set up a proportion. I could say, well, if 45 out of 100 is my probability, then how many am I going to get out of 80? I could do that. But since they give us a decimal, we might as well just say that 45% or 0.45 of or times our songs gives us our answer, right? So if we have 0.45, which is 45% of our songs are pop songs, then 45% of 80 is, put that in your calculator, and you get 36. You have 36 pop songs. And in my opinion, that's just easier than trying to solve this proportion. You're still going to get 36 if you solve the proportion, but I think it's easier just to, since they gave you a decimal, or if they give you a decimal percent, you just have to multiply that to the number of songs you have. All right, so the last thing we're going to do is I'm going to show you the difference between theoretical and experimental probability. And so we have a number cube, which is a 6-sided die that's been rolled 50 times, and the results are on this brown chart here. It says, what is the experimental probability of rolling a 2? So the probability of rolling a 2 based on the experimental probability, based on our observations, is that we rolled 4 2s out of the 50. Which I know they rolled 50 times. And so that's going to reduce to 2 over 25. That's my experimental probability. But when you roll a number cube, and you guys probably didn't know this, all the numbers are equally likely. So the theoretical probability should be of rolling a 2. Well, if there's 1 2 out of 6 numbers, then it should just be 1/6. I guess we don't need this spot here because that doesn't reduce. So you can see the theoretical probability is oftentimes different from the experimental probability. Again, experimental probability is based on observations, and we rolled the dice 50 times, and that's what we got. Theoretical probability is based on theory. We know we should get the same number. Whoops, that's not supposed to have an E right there. There, theory. We should get the same number of 2s as we do every other number. They're all equally likely. And then example C says the number cube is then rolled 300 times. What do you notice when you compare the results? Well, when you roll it 50 times, you can see our numbers are kind of all sporadically out here. They're all kind of all over the place. If you roll it more times, you can see it's more even, isn't it? And so the more observations you have, the better the results, because we're going to start to get that theoretical probability. It's not quite, they're not all quite exactly the same, but the more observations you have, the more times you roll it, the more likely it is to get to that theoretical probability of 1/6 for every single number. That's what our probability should be, is that the odds of rolling a 1, 1/6. The odds of rolling a 6, 1/6. The odds of rolling a 5, also 1/6. All right, let's finish up with a few homework questions. I've done quite a bit in these notes for you guys. Number 25 says the bar graph shows the results of spinning the spinner 200 times. Compare the theoretical and experimental probabilities. We just did this in the last example. So experimentally, a 4 was spun 37 times out of the 200. And so the experimental probability should be 37. 4 was spun 37 out of 200 times. And that's 18.5%. But since this spinner has all equally likely spaces, right, all the spaces are the same size, the odds of spinning any one of these numbers should actually just be 1/5. All these numbers have the same probability of being rolled theoretically. So the theoretical probability is 1/5, which is the same as 20%. So we rolled it 200 times. You can see the probabilities are actually pretty close. If I rolled it 200 more times, I would probably get even closer to 20%. But I know theoretically, all these numbers have a 1/5 chance of being rolled. When I actually do the experiment, okay, I was pretty close. 18.5% is pretty close to 20. Last one, number 33. I like this example because we're rolling two dice now. You roll a pair of number cubes. You roll them 60 times. The theoretical and experimental probabilities are shown. So I don't know if you knew this or not, but you're a lot more likely to get one of these numbers when you roll two dice than you are to get a 2 or a 12. A 2 and a 12 are the least likely numbers. And if you think about it, the only way that you can roll a 2 is by getting a 1 on the first dice and a 1 on the second dice. And same for 12. You have to get a 6 and then a 6. If I want to roll a 7, for example, well, I could get a 1 and a 6 would work, or a 2 and a 5, or a 3 and a 4, or a 4 and a 3, or a 5 and a 2, or a 6 and a 1. There's a lot of different ways I can roll a 7. So 7's actually the highest probability number that you can roll when you're rolling a pair or two number cubes. 2 and 12 are the least likely numbers to get rolled. And of course, you can't roll a 1 because, well, the smallest number you can get is a 2. If you roll 1 and 1, that's actually a 2. So it says, which sum would you expect to be the most likely after 500 trials, 1,000 trials, and 10,000 trials? Well, we rolled 60 times. And so if we rolled 500, 1,000, or 10,000 times, we're going to see that theoretical probability, which they did in blue. We're going to see that. So you can see the 7's the highest probability number theoretically that's rolled. And so 7, it would change. My guess is our experiment would change from a 6 being the highest to then a 7, because we're going to see that theoretical probability. So as the number of trials increases, we start to see 7 is going to be the most likely number. And then it says, explain how the experimental probability is related to the theoretical probability. As the experiment is repeated over and over, the experimental probability is going to approach the theoretical probability, just like we mentioned.